Hi everyone, welcome to Hamamatsu's YouTube channel. Today I'll be talking about LiDAR technologies. LiDAR is changing our lives every day, from factory automation to the robotic vacuums used in our homes, all the way to the promise of autonomous technology for the self-driving cars. All of this are made possible with adoption of LiDAR, which uses light for range measurements and velocity measurements. Today, I'd like to demo the optical module with Hamamatsu sensor and detectors used in LiDAR. First, I'll do an overview of LiDAR concepts. Then I would like to go through the selection criteria for detectors and sources. LiDAR, short for light detection and ranging. There are two concepts. One is the time of flight concept, which calculates distance using the time it takes for light to travel to the target and back. The other is FMCW, or frequency modulated continuous wave concept, that look at the frequency of the emitted and returned light to calculate distance and velocity. Due to time limit today, I will focus only on time-of-flight LiDAR concepts. In time-of-flight LiDAR, optical design can be complex. The light source and detectors in these designs affect multiple parameters such as cost, field of view, frame rate, detection range, and more. At the moment, there are two wavelengths of interest, which are 905 nanometer and 1550 nanometer. For 905 nanometer LiDAR, pulse laser diode are the most common source. When selecting the right laser diode, one must consider some key parameters. For example, to achieve a long detection range, laser diode should have high peak power when operated at short pulse conditions. It should also have high laser efficiency to reduce heat and power consumptions. The laser beam's quality is critical. Using a laser beam with sharp near field pattern and uniform far field pattern helps reduce range loss and measurement errors. The quality of laser is even more important for 1D laser array designs, which requires a sharp near field pattern to minimize the element-to-element interference. In a flash LiDAR concept, a large area of interest is illuminated with a flash of light. The most common light source is VCSEL, or vertical cavity surface-emitting laser. It emits light perpendicular to the mounting surface instead of parallel, unlike edge-emitting laser diodes. A VCSEL's key advantage is that it offers uniform illumination in a circular pattern with low speckle. However, the main challenge is to produce VCSELs with high power output that's equivalent to laser diodes. Selecting the right photodetectors can be complicated, mainly because of the vast number of choices. Unlike other suppliers that offers one or two technologies, Hamamatsu offers a complete family of silicon and InGaAs solutions, including pin diodes, avalanche diodes, silicon photomultipliers, and single photon avalanche diodes. The best way to show the difference between detectors is by using a simple setup here. Here is a model moving car with Hamamatsu's module mounted in the back. Inside this optical module, there's three different detectors: APD, SIPM, and SPAD. In the front of the module, we have three different settings: aperture settings, bandpass filter settings, and neutral density filter settings. The neutral density filter reduces the light intensity emitted from the laser diode built in within the module. The bandpass filter is necessary to reduce the effect of ambient noise entering the photodetectors. Changing the aperture size allows more or less light to be collected by the photodetectors built inside the module. The purpose of the lens settings is to simulate the best conditions for the demo here. Setting up this module is very simple. Just plug in the AC adapter that comes with the module, plus connecting the four outputs to the oscilloscope. The first three outputs is going to be for the built-in detectors, and the fourth one is to display the laser diode trigger. After connecting the wires to the oscilloscope, we now turn on the power switch, then turn on the visible laser switch that help align the module to the target of interest, which is going to be the model car. With the module turned on and active, we can now turn on the oscilloscope. With the preset display settings, we can see the three different displays on the scope representing APDs, SIPM, and SPAD, which is the force output representing the laser dial. Now let's focus on what's being displayed on the scope. What you're seeing on the scope is the raw output from three different detectors. The yellow on the top represents the APD output, the blue in the middle represents the SIPM or MPPC output, and the magenta color at the bottom is the SPAD or SPPC output. There's also a trigger output from the laser diode that's shown on the top as a grain waveform. As the toy car moves closer and farther away, the time domain of the waveform shifts left and right. The change in the time domain is used to calculate the distance. The amplitude of the waveform also changes as the car moves closer and farther. As it moves closer, more light is reflected back to the sensor. Therefore, amplitude increases. And when the target moves farther away, less light reflected and detected. Therefore, the amplitude of the sensor decreases. Using the simple demo, and by focusing on one frame, looking at the waveform capture on the left, we can now explain the difference between detectors. APD, or avalanche photodiode, traditional detector that has internal gain of around 100. Its low internal gain is very clearly observed as the output waveform from the demo, especially when the target is farther away. The low light level reflection causes APD waveform's amplitude or light intensity detected to be much lower. Because of this limitation, for longer range LiDAR designs, and to detect low light levels, APD must used with a low noise and high gain amplifier circuit. This means the readout circuit design will be complex versus other detectors, and especially when APD elements are needed to improve LiDAR system's field of view or frame rate. Since operating voltage and temperature sensitivity of APD are also higher, heat generation and power consumption can also pose challenges when more APD elements are added. Despite challenges of APDs, it is still the most popular and proven detector used in many first generation of LiDAR systems today. As more of these designs become commercialized, the detector cost should decrease, making LiDAR systems even more affordable. MPPC or SPPM is a more recent technology that's much higher gain than APDs. This advantage can simplify the readout circuit design, especially for wide field of view and high frame rate system requires 1D or 2D array of detectors. The benefit of high internal gain is shown on the demo's output waveform. Even when the target is farther away, the amplitude of the light detected is barely decreasing. One challenge, however, is the longer recovery time or tail of MPPC versus APD. This phenomenon is caused by the quenching resistor of the MPPC and the trapped carrier inside the silicon structure due to the high intensity light illumination. Pole zero cancellation and fast output from such detector are useless because this phenomenon is mainly due to the internal carrier saturations. The key factor, along with the number of microcells of MPPC, limits its dynamic range, therefore can cause LiDAR design headaches, such as figuring out how to treat signal received from high reflective targets that cause the saturation to the detector itself. As the detection efficiency of MPPC continue to improve, the range of LiDAR system can exceed that of APDs, making MPPC a good alternative to consider for the next generation of LiDAR designs. SPPC or SPAD is different from APDs or MPPCs. Unlike other detectors in which the intensity of light can be measured with one return, a SPAD is basically a single microcell of MPPC that can only detect if light is there or not. As you see from the waveform of the demo, the SPAD waveform amplitude does not change with the target when it moves farther or closer. To get intensity information from a SPAD, one must take multiple shots and use histogram analysis. Each SPAD element can be very small, in tens of micrometers, acting as a very small pixel but with very high internal gain and low noise detector. This technology is perfect for flash LiDAR concept when a high-resolution array is required to acquire best image resolution or angular resolution. One challenge is the complexity introduced by the readout electronics, which is very simple when fewer SPAD elements are needed, but can be very complex when a high density of SPADs are being made into a 2D or 2D array. Reading the output from thousands of SPAD elements at very high speed and performing histogram analysis to acquire return light intensity info can be very challenging. As the demo show, each LiDAR design is unique, depends on the different detectors selected. Hamamatsu have all three photodetector technology. Therefore, it's easier to make the right selection earlier than making more modifications later. With more LiDAR concept shifting from prototype to production, Hamamatsu's offering is also evolving. From the detector and light source company, we're now also offering an integrated solution such as assemblies and modules. One example is in front of me with a little compact module that has both detector and sources integrated as one. To operate a light source, a customer must design a driver circuit, provides proper operating conditions to the laser. An example circuit is demonstrated by Hamamatsu's macro high-speed pulse laser assembly or macro HPL assembly. This compact package integrates the laser and its driver as one. However, we understand that requirements can vary depends on the scanning or flash technique. When multiple channels or PLDs are used, the spacing between each element or laser driving condition can also vary greatly from design to design. When using photodetectors in LiDAR, analog output is now usable without a series of signal processing circuits such as amplifiers, filters, or other complex front-end electronics. Depends on the ambient noise, detector design, and LiDAR system requirements. The circuit requirements can be unique, challenging, bulky, and costly. This is why highly customizable application-specific integrated circuit, or ASIC, is becoming popular. For LiDAR, since every ASIC design is unique, Hamamatsu have the ability to work with customers to integrate complicated functions as one compact and ASIC and detector chip. Some examples of the ASIC function, such as the TDC, time to digital conversion circuit, or TOT, time over threshold circuit, are the two most common ones that are providing timing and intensity information about the target. Then there are many unique circuits, customized per user requirements to improve signal-to-noise ratio, correcting the range error to counter the effect of ambient noise, or stronger reflection from highly reflective targets. The ASIC designs can quickly become complicated for high-resolution scanning or flash LiDAR systems, when 1D or 2D array of detectors are needed, and each detector element requires its own ASIC chip, which means more sophisticated bonding technology, such as direct wire bonding or 3D stack bonding. By integrating detectors and light sources together with the respective electronics into a compact package, such as the module shown here, what we can do now is taking the burden of designing and manufacturing complex optical assemblies from LiDAR companies, allowing them to focus on higher-level system challenges. Such integration capability also allow Hamamatsu to take on the automotive reliability requirements for the whole assembly or module, not just the detector or light source separately. This would reduce the burden at high-volume commercialization stage, when LiDAR manufacturer can now be supplied with one part that's pre-qualified using strict automotive test standards instead of having to qualify every component by itself. The best way to demonstrate the performance and compactness of such integrated assembly is through a simple rangefinder here. To operate this rangefinder is very easy. All you have to do is turn on the system by pressing down the power button, then turn on the guide light, allowing it to aim at the target of interest. Next, click on the measurement button and you can get the distance to the target with an easy click. The distance reading is calculated through the time of flight method, and the measured range can be very accurate and precise. This rangefinder contains both emitter and detector assemblies. The emitter is the macro HPL assembly, as mentioned before, and the detector assembly includes a fixed gain APD and is integrated TIA. Other components such as signal processing circuit, display, and more are also included. There are other innovative and complex designs addressing the need of different industry and markets, such as the drones that deliver packages, the robotic vacuums that are used in our homes, and the different LiDAR system enabling the self-driving cars for fleet vehicles, consumer vehicles, and commercial vehicles. With many LiDAR applications, each one requires a unique design. More than 90% of Hamamatsu products are customized solutions. If you're a LiDAR technology company and is interested to talk about your LiDAR detector and light source needs, please reach out to us. Thank you for watching, and I hope to hear from you soon.